So welcome to the CSRC Colloquium. So I'm introducing Charles. He's my postdoc here in the math department. He did his PhD in physics officially, but did a lot of more applied math on that thesis. He's going to talk about multivariate self-similarity, estimation of self-similarity exponents, and biomedical applications. The floor is yours.
So yes, I am postdoc. I arrived in California 4 months ago and defended my PhD in last October. It was on multivariate self-similarity in France. And today I will present some parts of this work. I will show how to model and analyze multivariate self-similarity, and how to use the presented tools on biomedical data. First of all, before to talk about multivariate self-similarity, I will talk about univariate self-similarity for didactism. And before to talk about self-similarity, I will present the idea beyond self-similarity, the physical idea, which is scale invariance. Here is an illustration of scale invariance. This is the Barnsley firm. So if you take a leaf of this firm, you obtain a new firm with some rotation and everything, which is similar to the previous firm. And if you take a leaf of this new firm, you obtain a new firm, which is similar to the previous one. This firm is said scale invariant, because it has the same behavior at different scales. We can retrieve the same idea behind signals. A signal is scale invariant if it has the same exact or more usually statistical properties at all scales. Scale invariance is an interesting phenomenon that has been observed in very various fields in real-world data. For instance, the stock prices, the brain activity, for instance, measured from electroencephalogram, internet traffic, which is the number of bytes or packets as a function of time, or in stilometry, when we quantify a novel by for instance, the number of words as a function of the sentence. These are all scale invariant signals, and it is thus important to model this kind of signals. And the scale invariance can be mathematically modeled by self-similarity. A time series is said self-similar if when we dilate it in time by a factor a and in magnitude by a factor a to h, we obtain a new signal, a new time series on the right, which has the same statistical properties. And it is still true for any time dilation factor a, called the scale. Mathematically, it can be written as a finite dimensional distribution equality, where the dilation magnitude a to h. So yeah, an inequality that is controlled entirely by a single parameter, the self-similarity parameter h. And thus, in practice, it is important to estimate this parameter from a finite size signal.
So to use the independent variable, whatever it may represent.
The h? Sorry.
No, the t is the independent
it's
variable.
the time.
It's time. And
yeah, it's time. So yeah, using in stilometry, it can be the sentence. It's just the time unity, but it can be anything, an index, a continuous index. So we want to estimate h. So first of all, we need a model for self-similarity. And the most used model in the literature is the fractional Brownian motion, which is a self-similar Gaussian process with stationary increments, with variance behaving as a power law with respect to time, with exponent depending on the parameter h. This process has interesting properties since the covariance function of this process behaves as a mixture of power law with respect to time, with exponent depending on the h, and the rugosity of the trajectories are entirely controlled by the self-similarity parameter h. The higher h, the smoother the trajectory. Now that we have this model, we want to estimate the age from this model. And to this end, we can perform the wavelet transform of the fractional Brownian motion. This is the scalar product of the time series with the mother wavelet, which is translated in time by a factor k and dilated in magnitude by a factor 2j. We thus obtain at each time k and each scale j a real-valued wavelet coefficients. And then we can compute the wavelet spectrum, which is the variance at each scale j of the wavelet coefficients. So this is a function of the scale 2j, and it has an interesting property. Since for a self-similar process, it behaves as a power law with respect to scale, with exponent depending on age. And thus, in a log-log diagram, we obtain a linear function. We can estimate by linear regression the parameter age, illustrated here. So at this point, we have a complete model and a way to analyze this process, but it's only to analyze univariate self-similarity. And in real world, many systems can be driven by a collection of signals. We just have multivariate signals. For instance, in electroencephalography, we can obtain the brain activity at different regions of the brain, the same brain. Or in stereometry, you can quantify a novel by the number of words, but also the number of letters or the number of commas as a function of the sentence. So these are multivariate signals, and the question is, should we perform univariate self-similarity analysis of each signal, or one single multivariate analysis of the collection of signals? I will just present first the model of the multivariate self-similarity. The first approach, natural extension of the univariate self-similarity, is to consider a collection of fractional Brownian motions. So if we have m signals, we have m fractional Brownian motions with possibly different parameter hm, and they are correlated by a matrix signal. And thus, each time series verifies a univariate self-similarity relation. But this model amounts to the case, particular case, of fractional Brownian motions that are mixed by a mixing matrix W, which is identity. It doesn't change anything, but it suggests to replace the matrix W by any real-valued and invertible matrix W. Thus, we obtain m time series, and each time series is a linear mixing of correlated fractional Brownian motions. And it is interesting because this new collection of signals satisfies a new new relation of multivariate self-similarity, which is a finite dimensional distribution equality, where the dilation in magnitude is now a matrix A to H double bar. And H double bar is a matrix depending on the mixing, both the mixing matrix W and the self-similarity parameters H. We just aim to analyze such a process.
So you are making the assumption that each signal is independent.
Yeah.
No,
No.
yeah, those ones.
No, they are correlated by a covariance matrix.
What? So then those ones are supposed to be independent.
No, it can be correlation everywhere.
I mean, I understand that those ones are correlated because it's a mix of the other ones, but the other ones.
No, this one are correlated, then they are mixed, so it's mixed and correlated fractional Brownian motion. So you have three parameters. You have the self-similarity parameters and the correlation and mixing. So, so the fact is, in the end, so yeah, the correlation doesn't change anything to the self-similarity parameters, but here each time series will be parametered by all the self-similarity parameters. So the mixing does not involve correlation.
Your H1, H2, Hm, those ones are supposed to be independent.
The exponents?
Yeah.
Yeah, it's not. They are not random variable. They are just they are deterministic. So they are selected independently.
So, I mean, but you can't define in the outputs, there's no way to define individual age for each output, is what you're saying. It's some mixture of the characteristics for the different age parameters that are found in these.
I'm not sure to understand the question. So
Yeah, it's more of a comment. I'm just trying to understand it. I mean, it's clear what H means in the
Yeah.
univariate case. But here on the right-hand side, you kind of have a bunch of messy functions that have these sort of different scales, right?
Yeah. So in practice, So in the example of you will understand it. In electroencephalography, for instance, you can consider maybe that each signal is univariate self-similar. It has you have this scale invariance with a self-similarity parameter, and maybe a univariate analysis of each signal is a good idea. But in practice, maybe there are mixture of fractal signals, and it happens. So just to give an idea, on the brain, if you take the data, for instance, on the scalp, we will have the conduction that lead to mixture between the original signals. And thus, you will not have a perfect fractal signals. We'll have a mixture of all sources. So here, you can consider that here are your sources that are scale invariant, and what you observe, what you measure is not exactly the same. And
so in that case, you're saying there's, for example, a bunch of current dipoles in the brain that each can have an individual different H value.
Yeah, at the sources, maybe, but not at the measured signals.
Following that remark, what's your final goal? Is it to find the age of each one?
To find the original age.
Find the age of the potential sources that are behind. Those sources might be independent, but you measure correlated things.
So these sources are this one. So we want to estimate the underlying self-similarity parameters. So we have some observed signals, and we want the underlying.
Those ones are correlated.
The signals,
those ones.
Yeah.
So it's not the independent sources.
The sources are not necessarily independent. You can have sources with different scale invariant behavior. It's independent scale behavior, but not independent signals.
So there's some correlation between the sources, but each one can be assigned a unique H value.
Yeah. So we want to estimate the M underlying self-similarity parameters, and we can perform a wavelet transform, but now a multivariate wavelet transform, which is the wavelet transform of each time series with the same mother wavelet. And then, so we obtain at each scale J and each time key vector of real-valued wavelet coefficients. And we can compute the wavelet spectrum, which is at each scale J, the covariance of the wavelet coefficients across components. So it is a matrix of size m times m for each scale to J. And it has good behavior since in absence of mixing, first of all, if the process is self-similar, each coefficient of the wavelet spectrum will have a behavior, a power law behavior with respect to scale, with exponent depending on two self-similarity parameters. And thus, in a log-log diagram, we have m times m plus 1 over 2 linear functions. So in particular, we can just consider the diagonal coefficient of the wavelet spectrum. We'll have m power law behavior in log-log diagram, m linear functions, and each linear regression will provide an estimate of the parameter Hn. So at this point, for the case of no mixing, we can just it's natural. We can just take the wavelet spectrum of each signal is a univariate self-similarity analysis. We do it independently. So yeah, the signals are correlated, but we do the analysis independently. And since the scale invariant behavior are independent, we obtain the different Hn. But when they are mixing, now the coefficient of the wavelet spectrum behave as mixture of power laws with respect to scale, with exponents depending on all the the possible different self-similarity parameters. And thus, if we perform the linear regression in the log-log diagram, we don't obtain estimates of the different HM, we obtain estimates of the dominant parameter, because the mixture of power law is dominated by approximately the power law with the dominant exponent. So physically, it means that in the diagonal coefficient of the wavelet spectrum, because of the mixing, you will only retrieve the smoothest behavior of the different signals.
So suppose you have two H values that are almost the same, correspond to almost the same amount.
Yeah, if they are equal, then the univariate estimate will be a good estimator. So I will analyze the estimation performance after. So to overcome this bias, it has been proposed to consider not consider the coefficient of the wavelet spectrum directly, but the eigenvalues of the wavelet spectrum. And it can be shown that asymptotically, for a self-similar process, each eigenvalues lambda m will behave as a power law with respect to scales with exponent depending on h. And thus now, by linear regression, we can estimate the different HM considering these eigenvalues. So now we obtain a good estimate. But in practice, this estimation has some limits since at each kj, the number of available wavelet coefficients is finite, and thus there is bias on the estimated eigenvalues. Indeed, the gap between the estimated eigenvalues is higher than the expected gap. And it's particularly important when the self-similarity parameters are equal. And in the case of wavelet transform, there is different number of wavelet coefficients at each scale. If there are some 4 coefficients at the maximum scale, there are 8 coefficients at the scale beneath and 16 at the case beneath again. So the gap between the estimated eigenvalues will increase with the scale 2j. Here is an illustration where you can see the log eigenvalues in blue against the expected slope in dash black, and beneath the difference between the two functions. And you can see that the gap is more and more important with the scale, and thus we don't have linear function, and there will be bias in the linear regressions. To overcome this bias, we just propose the new method to correct the estimator. Another correction has already been proposed in another work using time-scale block bootstrap presampling, but this method has an important computational cost. And thus we propose an efficient method that consists to reproduce the bias of the eigenvalues across scales. The idea is to compute several wavelet spectra from the same number of wavelet coefficients. If at some maximum scale we have 4 coefficients, we compute 1 wavelet spectrum. We have twice more coefficients at the scale beneath, we compute 2 wavelet spectrum. At the scale beneath, 4 wavelet spectrum. So for all from 4 wavelet coefficients. Then we can compute the eigenvalues of all this matrix, and at each scale we can average the logarithm of the obtained eigenvalues. So it is important that if we do it, all the eigenvalues of this matrix will have the similar repulsion bias. And thus, if we compute the average of the logarithm of these eigenvalues, we obtain a structure function log lambda bar at each scale to j with similar repulsion bias. So here we can see in red this function against the expected slope, and beneath the difference between the two functions. And we can see that the log eigenvalues are biased since they are computed from a small number of wavelet coefficients, but they have the same bias at all scales, and thus they are linear. There's no gap increasing with scales. And finally, we we expect that the bias will be reduced. So to better understand the idea, here are the non-corrected structure function and the corrected structure functions with the difference between the structure function and the expected stuff. And we can see that with no correction, the bias is increasing across case, and thus we don't have linear functions. While in our method, we have biased log and gun values, but linear. So we expect this method to give better estimates of the parameter HM. So to study the performance, we consider the context of large sample sizes n and large scales to j. So the scales are increasing with the sample size, and the speed of convergence of the scales is controlled by a sequence an, which is similar to a power of n, where the power of beta depends on the difference between the self-similar parameters. The more different the parameters, the higher beta. And beta is a parameter to control the trade-off between variance and bias. In this context, we have shown that we have shown two important results. First, the different estimators are consistent. The univariate estimator is consistent if there is no mixing. And the multivariate estimators, corrected or not corrected, are consistent in any case, mixing or not. And we can also show that if the eigenvalues are asymptotically distant, the bias corrected estimator will asymptotically has a multivariate normal law. So we can wonder what are the finite size effects on these different behaviors, and what are the impact of the parameters HM, correlation sigma, and mixing W on the correlation of the estimator. And so to study the performance, we consider simulation. So we consider 1,000 realization of multivariate fractional Brownian motions of 6 components with a fixed correlation for different sample sizes and scales increasing with the sample sizes. And we consider 4 different configurations that I will show one by one. So in this configuration, you can have mixing or no mixing, or self-similarity parameters that are all equal or all different. The performance is measured in terms of bias, covariance, and mean squared error. And since the estimators are vectors, these measures are matrix. So to measure the performance, we consider the spectral norm of this matrix. This matrix is so first, we analyze the distribution of the estimator. Here are the quantile plots of the Mahalanobis distance of the estimator against a chi-squared distribution with m degrees of freedom. So if the blue points, the quantile line are aligned with the diagonal, we are close to a multivariate normal law. You can see the quantile plots for the sample sizes increasing for left to right, and for the different configurations from top to bottom. And we can see that even at small, for any configuration and even at small sample size, the distribution of the estimator is well approximated by a multivariate normal law. So now we can compare the performances of the different estimators. First, we consider the general case of when there is no mixing and self-similarity parameters all different in terms of bias, covariance, and mean squared error for the different estimator. So we can see that the univariate estimator is biased by the dominant parameter, as I said before. And the multivariate estimator will have a better performance in terms of bias, but also in terms of covariance. So overall, it is better to use the multivariate estimator, which has similar performance. Now we can consider, as you said, the particular case where the self-similarity parameters are all equal. And we can see that in this case, the multivariate estimator is biased. But the univariate estimator is less biased because it estimates the dominant parameter and they are all equal. It just related to the particularity of the case. And the corrected estimator will have a better performance. And in terms of covariance, the multivariate estimator will be better than the univariate one. So overall, the corrected multivariate estimator has the best performance. Now we can consider the case when there is no mixing. So this is the univariate case. The parameters are all different. We can see that in absence of mixing, the univariate estimator has an important advantage. But in terms of covariance, it's less. The performance are less good. So overall, the performance of all the estimators are similar. It is interesting to see that the performance of the multivariate estimators are the same to the case when there is no mixing. So it doesn't change anything for the multivariate estimators. The difference is for the univariate estimator. And overall, there is a bias. There is a trade-off between the bias and the covariance when you use univariate or multivariate estimator. Finally, we can consider the particular case where there is no mixing and parameters all equal. In this case, we just obtain performances similar to the case when there is mixing. So it means that when the parameters are all equal, the estimator are robust to the presence of mixing. To sum up these results, we can see that in any configurations, the corrected multivariate estimator has similar or quite better performance than the other estimators. So it's more interesting to use this one if you don't have any prior on the parameters. To conclude this analysis of performance, we can look at the correlation in the general case of no mixing and parameters all different. We can see here the correlation of the pairs of parameters for the different sample sizes n, and we can see that there can be an important bias for the univariate estimator, but even a small sample size, the multivariate estimator have little correlation. And we can conclude the same thing when there is no mixing. So this is not, this doesn't depend on the presence of mixing. So now that we analyze the performance of the different estimators, I propose to show how to apply it to real-world data. Two applications has been performed on biomedical data. So there's a paper on the detection of dizziness from 4 varied physiological data. And here we present how to predict epileptic seizures from brain activity, multi-channel brain activity. So the data used here are from the THB MIT SCAD-BEG database available online. And that consists of 19 canals measured from 19 pairs of electrodes on the scalp of 8 pediatric subjects, sample at 256 Hz. And the goal to predict epileptic seizure is to detect a pre-ictal state, which is a period just before seizure state, against an interictal state that is far away from any seizure. We will consider the classification of the detection of the state on the 19 varied windows of 2 minutes of these canals. Channels, sorry. First of all, we analyze the scale invariance of the data. Here we can see for an interictal window at the top and the pre-ictal window at the bottom, the different structure functions for the univariate on the left, multivariate estimator on the middle, and corrected multivariate estimator on the right of the previous data. And we can see a power law of these different functions from scale 2 to 1 to 2 to 8. So from frequencies ranging from 0.5 Hz to 85 Hz. It means that there is both a univariate and multivariate scale invariant behavior in this data. Thus, we can perform a linear regression, and we perform the linear regression from 10 to 85 Hertz, according to the literature on the subject. And so here we can see the obtained univariate estimates on the left and corrected estimates on the right for the 8 different patients across all the interactal states in green and all the projectile states in red. And we can see first that for each patient there is differences between the interactal and projectile states in terms of distribution of the estimator, and the differences between these states are different from a patient to another patient, suggesting that it is important to perform the analysis per patient. So now to quantify the differences, we can see here the Wilcoxon test p-values between the interactal and projectile states for the different estimator. So in black, the univariate, in blue, the multivariate, and the corrected one in red. Compared to the Benjamin-Hochberg thresholds for the multiple comparison for the 8 patients. And we can see that that the differences between the interactal and projectile cells are significant for all the estimators and for all patients, but they are more significant for the corrected estimators. So note that we have this quantification. We can perform a classification using these estimators. And to do this, we propose an overall procedure. The idea is to define a reference distribution using 100 interactal windows. So we compute the estimates related to these windows. We obtain the reference distribution of the HM under the null hypothesis. And then to classify a window, we compute the related estimate HM, and then we can compute the p-values of this estimate according to the reference distribution. Finally, with this p-value, we can perform the Benjamin-Hochberg procedure to compute a rejection decision of the projectile or interactal states for some threshold. So in this procedure, we can consider either the univariate estimates or the corrected multivariate estimates, or the m times m plus 1 over 2 classic multivariate estimates, which are, reminded, the linear regression on all the coefficients of the wavelet spectrum. So it's another way to take the multivariate behavior, because you take all the correlation in the wavelet domain. So to analyze the performance of this classification procedure, here are the work curves for the different estimator and for, on all the patients. We can see the power, so the well-detected projectile states against the wrongly detected projectile states. And you also have the area under the curve of the different curves. And we can see that the performance of the multivariate estimators are better than the performance of the univariate estimators for the different patients. But the advantage of the corrected multivariate estimator is that it is based on only m features instead of m times m plus 1 over 2 features, because we use the eigenvalues instead of all the coefficients of the wavelet spectrum. So to conclude, today, so I presented how to estimate the multivariate self-similarity parameters. So I particularly introduced a new method which is robust to the regression bias that I presented. MATLAB toolbox is available on my GitHub with all the tools for estimation. And other works have also been considered. So particularly the clustering. So as you said, so maybe in the self-similarity parameters, so the vector of self-similarity parameters, maybe some signals have the same scale invariant behavior. So maybe there are like 20 or 30 signals, but only 2 different scale invariant behavior. So it can be interesting to count the number of different parameters in H bar. And we propose some strategy of clustering using, we know that there is a multivariate normal behavior, so we can use hypothesis testing procedure combined with spectral clustering on graphs. You can discuss if you're interested. And another work is the high dimension, because in practice the number of components can be very large compared to the sample size. And in this case, we don't consider a double limit, but a triple limit, where the number of components is also going to infinity with the sample size and scales. So in this case, we also consider some hypothesis testing procedure if you're interested. So here are some papers, if you want to read. There's paper on estimation, 2 papers on the biomedical applications, and there are also papers on the other works I didn't present. And many scale invariant. Thanks for your attention. Yeah.
So is there any promise in more recent research? I mean, it sounds like this is going to be applied in a clinical setting. It's got to be calibrated for every different patient, right?
Yeah.
Is there anything, are you pursuing anything to try to get around that issue? I mean, do you think there's something universal that can be detected in the self-similarities of these signals that would be the same for all human beings?
No, unfortunately, as I have shown it on. So yeah, so I was expecting that maybe it's more like you have smoother signals when you are in intellectual states, and yeah, more rugosity. But unfortunately, you can see that like in the box plot, you can see that it's very different, because here it's exactly the opposite between the two versions. So yeah, I saw some. There's some papers in the on univariate scale invariance. So typically they took like 2 or 3 signals, and they can see that maybe there's some universal behavior. But when you take all the signals and the multivariate, you do the multivariate analysis, you don't have a universal pattern. So maybe in some other data, maybe not for. So here it's just for epileptic seizure prediction, but maybe for other behavior. But
how consistently can they place the electrodes for these experiments?
The
consistency of electrode placement.
Oh.
Does that affect what you see? I mean, I'm just trying to grasp why it's so different for different patients. So, you know, I mean, if they're sloppy with where they put the electrodes, that could influence what you see.
Okay.
I think there's a little bit of bias in the position, but
It's just because people's brains work differently.
Yeah,
Epileptics.
I think so. I cannot say anything about the way they.
there's different types of epilepsies. So you have.
So yeah, it's interesting, because yeah, you can have some delay between the. So that's the question.
I mean, there's different types of epilepsy.
Types. Sorry, I said it was time.
So does that analysis take care of that, or I mean, does the patient?
No. So the data I use is just intractable seizures, but you don't have a specificity on the kind of seizure. So it's for general seizure. Maybe for some type, you can have a more specific analysis. Yeah, maybe. Yeah. No, it's general study, because we do not have. Yeah. But yeah. So all the problem is to find data. Because here, yeah, it's the public database very used for this, but yeah, maybe the specificity of the type, it can be interesting.
Regarding the wavelet transform,
yeah,
does it depend on which other wavelet you use?
So technically no. So we can show that. So I use the double sheet wavelets. We can show that it doesn't depend on the number of vanishing moments. Vanishing moments.
Certain number of vanishing moments.
Yeah.
It's fixed. That should depend.
Here it's fixed to 3, but if you take 2, 3, or 10, it doesn't change anything in the performance.
Oh, you mean in terms of related to your analysis technique?
Yeah.
Okay. Oh, yeah, okay, makes sense. Yeah.
Vanishing moments doesn't change anything. The type of wavelets, so we use the double sheets because it's perfect, it's regular, it's all you want. So technically, yeah, maybe some, I don't know if other wavelet can have some advantage, but for all the theoretical studies, it's better to have all the expected properties and to be sure that
there's a potential issue, which is you are using the wavelet transform with the Dan sampling, right?
Yeah, the dyadic decomposition.
That could be an issue because it's not translation invariant. If your signal is just translated by 1, you might get a wavelet transform that's quite different. So what is the influence of that on your analysis?
Yeah, I don't know if there is a difference because here we use the, maybe so.
And you compute those wavelet spectrum.
Yeah, but the important things here is not the wavelet spectrum, but the behavior across scales. So maybe the translation will be repeated at different scale. So I'm not sure that there will be difference.
So there's probably a difference, but I'm not 100% sure. Because that's a well-known thing when you do target detection, for example, right? You don't want to use any Dan sampling because that sometimes you can actually see things completely disappear in your analysis. So that using an n-decimated transform might be a better idea.
Yeah, I don't know because so the idea here was to only use this. Because it's more efficient to use this.
Yeah.
And that's why we did all this correction of operation bias and everything. So
yeah, but then maybe if you use non-decimated transform,
you have no problem.
Maybe
you don't have operation
you don't
bias
need
on
those
this.
things anymore.
No, you don't need this correction on the undecimated. So I don't know. Yeah, I never compared the two approaches. But...
Other questions? Okay, let's thank our speaker break.